Okay, I guess we get started. So your midterm was published. The results were published this morning. There is the distribution. The median is an 82.5. The average is quite a bit lower, but that's because of the, there were some results that were quite low. So it dragged the average down. I think the average was 76 or something like that. But the median's 82.5, which is quite good. Let's see. One of the questions has a wrong answer. So I forget which one it is. The last question, one of the variations has an incorrect solution. And I can't fix it because OnQ won't let me change, it won't let me fix the answer that's been handed back to you. Because you already wrote the test, it won't let me change the solution. So I'll have to post a solution for that question somewhere else, I guess. Yeah, that's all I want to say about that. I think you did quite well on it. So congratulations. Back to this function here from 2 lectures ago. So there was this toString method in the, for the list. Someone pointed out that there was a bug in the function, and there is. So here's the original function. That's the original size of the buffer that we're printing into. So as you print into that buffer, it should get smaller, right? But because it's declared as const, I can't change buff size inside the function. So what had happened before was I kept on using buff size everywhere, right? So that's the maximum number of characters that you'll print into the buffer. But because you're printing into it, that should get smaller and smaller each time. So the funny thing is if you run this, it actually seems to work. So if you use the demo program, everything seems fine, right? So if you compile it, run it, it actually seems to work. And it actually seems to produce the correct results. So if you look at the lists that are being printed here, the output should only be 31 characters long, because my buffer is 32, is an array of 32 cars. Right? If you look closely at the output, though, you'll see that some funny stuff's happening. Right? If you actually count the number of characters, the first one's fine. That's actually 31 characters long. Right? But if you look closely, there are some that are coming out that are longer than they ought to be. Right? And so something funny is, in fact, happening. Right? Now, the scary thing about this is it doesn't crash. The demo program doesn't crash, and there's no indication that there's an error, other than you have to look really closely at the output to see that there's a problem. You can get it to crash, but it takes some effort to do. So I'm not going to try to do that right now. The solution is to create another variable, which is the amount of space remaining in the buffer. Right? So buff remaining is the remaining buffer size. And every time you print into the buffer, right, if you get past the if statement, if you get past the return statement, you want to decrease the value of buff remaining. Right? Now, you have to be very careful when you do this. Right? If you put this line up here, right, so in other words, if you write that up there, right, you write buff remaining minus equals n. Right? Buff remaining is an unsigned type. Right? So it's unsigned here. Right? If you end up printing too many values into the buffer, then when you subtract n, right, that buff remaining becomes less than 0. Right? But it's unsigned. So that when it becomes less than 0, it becomes some gigantic number, right? Some huge number. So it becomes the size of, on my computer, it's a 64-bit int, right, which is enormous. Right? So you end up with some enormous value that you then end up plugging into buff size here, which is incorrect. Right? So these values should not be buff size. They should be buff remaining. And that should not be buff size. That should be buff remaining. Right? And then when you compile this one and run that one, and run the new version of the program, you'll see that that's better. Right? Now they're all coming out as 31 characters long. Right? And now it seems to be correct. Right? Now it seems to be correct. So that was that's the fix to the toString function in the list class. So I'll post that on OnQ sometime today. All right. Today's lecture is we're going to do some more simple node. We're going to create another simple data structure using nodes again. Oh, sorry, not from here. From the beginning. OK, so now I want to implement something called a queue. Right? Also using linked nodes. right? So that's a queue, right? A queue is just a line, right? So this is a real-life example of a queue, right? Now the data structure queue emulates this sort of thing, right? So there's someone in the front of the line, right? The person at the front of the line is the person who's going to be serviced next, right? When people come into the line, they enter from the back, right? So the person at the back of the queue, that's the person who will be serviced last, right? And so there's a notion of the element that's at the front of the queue and the element that's at the back of the queue, right? So in a queue, whenever something comes out of the queue, it comes out from the front, right? Whenever something enters the queue, it enters at the back, all right? So this is an ordinary queue. There's a type of queue called a priority queue where the elements that come out are the ones with the highest priority, not necessarily the ones at the front, right? But that's a separate story. All right, so front of the queue, back of the queue, right? Okay, now like a stack, a queue only classically supports only two operations, right? So the enqueue operation, right, that adds an element to the back of the queue, and dequeue removes the element from the front of the queue, right? And it's an error to dequeue an empty queue, right? So these are similar to stack, right? So stack enqueue is similar to push, right? Dequeue is similar to pop. It's just that they happen at the enqueuing happens at the back, right? And dequeuing happens at the front, right? Whereas in a stack, everything happens at the top. Okay, you can put in other operations, right? So normally a queue support, so if you went out and found a queue data structure, normally you'll find that there's other operations, right? So you can ask for the number of elements in the queue. You can ask if the queue is empty. Many queue implementations let you look at the front element of the queue without removing it. So that's called peek. A lot of stack implementations will let you do that too. So you can also peek at the top of a stack in many implementations. You might implement contains for a queue to find out if the queue contains a particular element, right? And the list goes on and on and on and on, right? You can add lots of different functions to a queue. Okay, so this is what it looks like in a picture. So F and B, so those are going to be pointers to the front and back element of the queue, right? So when you have an empty queue, they point to nothing, right? So they point to null. All right, so I'm going to do enqueue. In this case, the string A. I should have changed these to ints, but anyway, it's fine. So I'm going to enqueue the string A, right? So when you enqueue the string A, right, A appears at the front of the queue, and the front and the back both point to the same element, right? So that's going to be the element that's serviced first. So if you dequeue it, that's the one that comes out. And if you enqueue, you're going to add to the back, right, behind the element. Right, so if I enqueue the B, right, I add the B to the end of the queue, and then I move the back pointer. Right? If you enqueue a C, right, add the element to the back, and then move the back pointer. Notice that when I enqueue, in principle, the only thing that changes is the back pointer. Right? Right? Add the D, move the back pointer, add the E, move the back pointer. Move the back pointer. There we go. Right? So that's all that happens. Now when you dequeue, right, all the action happens at the front of the queue. Right? So when I dequeue, right? Okay, so this one's going to be a little bit confusing, right? So because of the way I drew it. I really should have made the front pointer move this way. Instead, I'm going to leave the front pointer where it is, right? Which is a little misleading. I should probably change that. Okay, so because it looks like the back pointer is moving, but it's not. So when I dequeue, the A is going to come out, right? And really, I should move the F to point to the B, but instead I'm drawing the, sorry. So dequeue, so everything, in this case, everything's sliding over, right? But we're not actually going to do that. I don't want to actually move elements. I want to move the front pointer to point to the next element, right? So I dequeue again, right? B is going to come out. It points to the C, right? Dequeue again, right? And you dequeue again, and they're both going to be pointing to the same element, right? If I dequeue one more time, the element comes out, and now the front and back both point to nothing. Right? So when you enqueue, in principle, everything happens at the back. Right? When you dequeue, in principle, everything happens at the front. So the queue is a FIFO data structure. So first in is the first out. Right? The first person in line is the first person to be serviced. Right? So that's the opposite of a stack. Right? So a stack is a LIFO data structure. Right? Last in, first out. And like a stack, these things turn out to be incredibly useful in computer science. Right? So you can imagine some sort of web service, right, where there's a queue of waiting people. Right? So online customer queues, these are implemented as queues. Right? Your web server uses a queue to service requests. Right? So a web server like Amazon runs has literally millions or hundreds of millions of requests coming in all the time. Right? It can only service one request at a time, so it puts all the requests in a queue, and they somehow get serviced. Your operating system has all sorts of queues in it because you use a queue to manage resources. Right? So you'll have a printer queue. Right? If 100 people try to print something to your printer, right, they all get into a line and they get serviced one at a time. Right? Your hard disk has a queue, or your hard disk or your solid state disk has a queue. Right? And the CPU has a queue. Right? It actually has a hardware queue in it because your CPU, again, can only service one process at a time. Right? So if you have lots of things running on your computer, each process gets a little bit of slice of time. They all get put into a queue, and they all get serviced one at a time. Network devices use queues to determine which packets to service. So on your router at home, right, typically video packets get serviced at a higher priority than other packets, right, because you don't want your video to be choppy. So those all get put into a bunch of queues. And there's a classic algorithm called breadth-first search that you use to search graph-like data structures. So you'll see this in 365 for sure. You might see it in 235. That's normally implemented using a queue. And if you want to look at it, right? Oh, sorry. Right. So the breadth-first search algorithm, right, uses a queue to actually implement the algorithm. All right. So here's an example from robotics. Now, the example I'm going to show you doesn't look like, is actually breadth-first search in disguise. So in robotics, there's a large body of research related to path planning. So you have a robot. It's supposed to be autonomous. It's starting somewhere. It needs to get somewhere in the world. Right? So that's the path planning. You want to find the sequence of moves that gets you to the goal. Right? So the way this problem is normally phrased, you're given a map of the environment, and you want to find a path between the starting point of the robot and some goal location where the robot doesn't pass through any obstacles. Right? So it doesn't go through any walls or hits any objects or things like that. Right? And so one approach to solve this problem stores the map as just a grid. Right? So there's your map. Right? The robot's going to start in the bottom left-hand corner, and it's going to try to go to the top right-hand corner. Right? You can think of this as being a maze if you wanted to. Right? The red squares are walls. Right? Anything that's white is open space, so that's space that the robot can travel in. So there's an algorithm, a very simple algorithm called the Wavefront Planner. And so the Wavefront Planner tries to find a path from here up to here. Right? So the way it works is anything that's free space, you label with a 0. Right? So anywhere the robot can move, you label with a 0. Anywhere the robot you can't move, you label with a 1. Right? The goal is labeled with a 2. Right? So up here, that's where I want to get to. And the start is just labeled somewhere, so you know where the robot's starting from. Right? All right, so the algorithm is very simple. Right? You start with the goal cell, so you start with label number 2. Right? While the start cell is unlabeled, right? So while the robot has not reached, while you have not labeled the start cell with a number, right? For every cell C with label L, right? For every cell Z connected to C with label 0, right? So in other words, for every cell connected to C that hasn't been visited yet, you're going to label that with another number. Right? This is easier when it'll be easier when I show you the picture. Right? And then you increment L. Okay, so this is what happens. So starting up here, right? Every cell connected to the 2 that had a label 0, right? So every cell connected to the 2 that has a label 0, and we're only looking at 4 connectivity, so we're not looking at 8 connectivity here, right? I'm going to mark with a 3, right? So I'm going to mark those with a 3, right? And now I want to repeat the process. Right? So every cell marked with a 3, every cell adjacent to 3 that's marked 0, I want to mark with a 4. right? Now the way you do this is you put the 3s into a queue, right? You take the first 3 out of the queue and you look at all the adjacent squares to that 3, right? And you mark them with a 4. Then you take the next element out of the queue, right? That's the 3. And you mark all the cells adjacent to it that are 0 with a 4, right? The queue is now empty, so now you put all the 4s into the queue. Right? So now the 4s go into the queue, the 5s go into the queue, then you dequeue them, process them, right? Eventually you end up over here, right? You keep going, you end up with something that looks like this, right? Now you can see why it's called the Wavefront Planner, right? So the explored cells move out in what's in like a wave coming out from the points, right? So you can see it sort of expands, right? And eventually you end up here, right? Where you're now going to label the start cell, right? So now on the next iteration, these cells here and this cell here, sorry, I should turn this on. This cell here, this cell here, and this cell here will be labeled with a 50. So the start cell becomes labeled, right? So that'll become a 50. Now to generate your path, you just work backwards, right? So you start at the starting cell, right? And while you're not at the goal, you move to any connected cell with the label having 1 smaller, right? So starting at the 50, I move to any square labeled 49. It doesn't matter how you pick it, right? So I could move here or here, right? Then at the 49, you move to any square labeled 48, so here or here, right? Now notice if I went here, the next move is to go to any cell with a 47, so it forces you to here, right? And then if you just trace that backwards, you're guaranteed to get back to the goal. Right? So this thing here is actually breadth first search, which was the algorithm that you can look up on the Wikipedia page. The easiest way to implement this algorithm is with a queue, right? So we're not done. So I actually want to look at the source code now for this queue class, or not class, this queue struct in C. All right, so not surprisingly, right, it's going to look a lot like the stack, right? So instead of a queue struct, instead of a stack struct, I'm going to make a queue struct here, right? So this is the header file, right? I have a function to initialize an empty queue, right? I have a function to free a queue. I've got a function to print a queue, right? That one tells me if the queue is empty. That one tells me the size of the queue. And NQ and DQ, well, these are going to be similar to push and pop from the stack, right, from Monday. Right. So we don't really need to look at, well, let's look at it. So all the way back at the top. Right, so again, I'm going to implement this using nodes, right? So I need a node struct, right? It doesn't matter that this thing's called node inside of queue, and it's also called node inside of stack, right? You're allowed to do that. So you're allowed to have the same structure defined in 2 different compilation units, right? As long as the 2 units don't, no, you're allowed to define them into 2 separate compilation units, right? So there's no, it doesn't matter that they have the same name, right? So I have a type def here, right, that says node is just a struct node, right? So instead of writing struct node everywhere, I can just write node, right? What does the node look like? Well, it stores an int value, right? And it has a pointer to the next node, right? So just like the stack from the other day. Now the queue structure changes a little bit, right? So the queue structure now, right? So in the stack we only had a pointer to the top of the stack, right? For the queue, I need to do something at the front of the queue, and I need to do something at the back of the queue, right? So I need to do something at the front when I dequeue, right? I need to do something at the back when I enqueue. So I need pointers to both of those nodes, right? So I need a pointer to the front node. I need a pointer to the back node, right? So all I've done is add 1 extra member to the structure, right? And similarly, I want to know how many elements are in the queue. Okay. So initialization is the same as initializing a stack, right? I want to allocate space for the queue, right? So we use malloc, right? We always remember malloc might fail, and if it does, I'm going to return null, right? So I can't initialize the queue, right? And then you want to initialize the members of the struct, right? So the front of the queue is null, right? The back of the queue is null, and there's no elements in the queue, right? So front and back will always be null when the queue is empty, right? Now, right, when the queue is empty, right? Okay. Size and is empty, those are simple, right? You just return the value stored in the struct, right? So the size of the queue is just queue size, right? Is it empty? Well, is queue size equal to 0, right? All right, now enqueue you have to be a little bit careful with. Okay, so if you compare this to the stack method, push, this one's a little bit longer because you have to deal with a special case. All right, so if I'm going to enqueue an element, right, I need to make a new node to hold the element, right? So that's the first thing I do. Right. Next, right, check if you could actually allocate space for the node, right? If not, return false, right, indicating that enqueuing failed. Right, so now I initialize the node, right? So the element I put into the node, right? And I start by saying that nNext is null, right? But remember, I'm enqueuing at the back, so that makes sense, right? So I have a queue of length 1, right? And I'm going to add a new element here. So that's going to be my new node, right? There's nothing back here, so that's going to point to null, right? So that's fine. But that's what I want to do, right? I want to hook up this node to the previous node here, right? Now, there's a special case you have to worry about, right? So in the empty queue, right, front and back are both pointing to null, right? So front, back, they're both null, right? Now remember, when you enqueue, you're normally always doing something with the back pointer, right? Normally you don't touch the front pointer, right? But when you put something into an empty queue, you have to touch the front pointer, right? You have to make the front pointer point to the element you added, right? Normally you don't, right? So now you have a special case here, right? Which is very easy to miss. It is extremely easy to miss this case, right? So if the queue is empty, I have to make sure to make the front of the queue point to that new node that I'm going to insert, right? So in other words, I'm going to insert the new node, right? And now I need to make sure that front points to that new node. Right? But normally you don't have to touch front, right? Normally you're only going to touch the back node. Right? So I'm going to touch the back node here, right, after the if statement. Right? So eventually I'm going to make the back pointer also point to that node. Right? But there's something else I have to do. Right? I need to make sure that I hook this node up to whatever was in front of it, if there is something, right? To whatever the old back of the queue was, right? So for example, in this case here, where you don't have an empty queue. So when you have a queue of size 1, right, so that's null. Front and back both point to here. Right? So in this case, when I insert a new node, right, I want to change this. I want to make this node point to the new node. Right? So what's that node? Well, that's just the old back of the queue. Right? So that's back next. Right? So back next now points to the new queue, new node. Right? And then you move back to point to here. Right? So that thing here is b.next, right, which I have to assign. Right? Which you do right there. Right? Now once you've added the new node, you have to remember to increase the size, right? Which is also surprisingly easy to forget to do. Right? And then you're done. Right? So this is a little bit trickier than when dealing with a stack. right? With a stack, we didn't have to, there's no special cases to deal with, right? Because everything always happens at the top of the stack. Okay, now what about dequeuing? Okay, so dequeue, not surprisingly, also has a special case. Right? Okay, so step one. It's an error to dequeue an empty queue, right? So I'm going to use an assert statement to catch that error. All right, so when I dequeue, right? So remember, when I remove this node, right, I want to return 1 back to the caller, but then I have to free the memory that's associated with that node, right? So I need a pointer to the current front of the node so that I can free it later on, right? Just like we did with the stack, right? I can't just use queue front, right? I can't, at the bottom, I can't say free queue front because the front of the queue is going to change, right? Queue front is going to point to the next element in the queue. Right? So I need a separate variable to refer to the old front of the queue. Right? I want to return the element that's sitting in the front of the queue, so I need to get that element out of the node, right, before I destroy the node. Right? And now I'm going to dequeue the element, and the way I'm going to dequeue the element is all I'm going to do is make f follow that pointer to point to the next node. Right? So I'm just going to make, normally I'm just going to make f point to here. Right? So down here, right, I'm just going to make f point to the new, to the next node in the sequence, right? So no, I just want to do this. I want to do that, right? And now you've got a queue of size 1, right? So I can decrease the size of the queue, and now I can free that front node, right? And so when I free that front node, that now disappears, right? And you've got a queue of size 1. All right, now there's another special case, right? So remember when you dequeue, everything happens at the front, right? So normally you only touch the front pointer. But there's a special case, right? So if I have a queue of size 1, right, I now have to touch the back pointer as well, right? Because when I take this element out, both the front and the back should point to nothing, right? If I don't make the back, if I don't set b to be equal to null, right, and I free that node, right, then whatever pointer is sitting in B is now invalid, right? So you want to be careful about that. So before I decrease the size of the queue, well, I guess you can do it afterwards, right? But if I'm going to check before I decrease the size of the queue, I want to check, is the current size of the queue 1, right? Is it 1? Right, if it's 1, I want to set the back pointer to be equal to null, right? Because I'm going to remove that node. Right? So queue back now becomes null. Right? So in other words, that now points to nothing. Right? Have we unhooked the front? No. Right? So the front, what do I say? Queue front equals front next. So that's fine. Right? That's queue front is equal to front next, which is also null. So that's good. Right? So that now becomes a pointer to null. Right? And now you've just got this plain old node hanging out, which you can now free. Right? And so now that node disappears. Right? And you now have an empty queue. Right? So you have to be very careful with these special cases, right? Normally when you're dequeuing, you're only worried about the front of the queue, right? But sometimes there is a case where you're worried about, where you have to also touch the back of the queue. Right? When you're enqueuing, normally you only touch the pointer at the back of the queue, right? Unless the queue is empty, right? In which case you now have to also touch the pointer at the front of the queue. Okay, any questions so far? All right, so a little bit more complicated than a stack, right? The next step from the queue is to actually implement an actual list, right? So now we can actually implement a list that behaves like the array list we had from last class, from 2 classes ago, right? But now it's all nodes instead of using an array, right? And so in that case, that's sort of a mix-up of a stack and a queue, kind of, sort of, right? But like the queue, there's going to be special cases when you have to deal with at the front and the back of the list. Right, so we'll keep that in mind for next class. Now, just like printing out a queue is the same as printing out a stack, right? You can use the exact same code. So you can either do it iteratively, like this. Right? Now remember, when you're working with a linked structure of nodes, there's always a pattern, right? If you want to iterate over all the nodes. Right? You start somewhere, so you just set a pointer to point to the starting node. Right? And then you loop as long as that pointer is not pointing to null. Right? Inside the loop, you just update the pointer each time, right? At the end of the loop. Right? N equals n next moves the pointer to the next node. Now, just like a stack, right? This is just a sequence of nodes, right? Nodes are recursive, they are structurally recursive, so you can write a recursive version of print, right? It's the exact same code as last time, right? So how do you print a node? Well, I print out front, then I print out all the nodes in the queue, and then I print out back. How do I print out the nodes in the queue? Well, I do it recursively, right? So if that node's not null, print out the element sitting in the queue, right? And then print out the rest of the queue, right? That's how you should read this recursive method, right? So when you call the method itself, it's just going to print, right, everything starting from the next node, right? Eventually, you'll reach the case where the node that you were asked to print doesn't exist, right? In which case, you don't have to print out anything, right? You just return. Okay. Any questions so far? Good. Demo program. So it's going to be the same as the stack demo program here, right? You make an empty queue. Print out is the queue empty or not, right? Print out the queue. Oh wait, else stack. Why is this? Oh, that's funny. Hang on, sir. This is actually the wrong program, but I don't know if I have the right one here. Queue demo. What do I have? Oh, I have the wrong one open. Okay, here we go. Queue demo. So make an empty queue. Test if the queue is empty. Should be, right? Print the queue. Enqueue 5 elements into the queue, and then I'm going to dequeue them and see what happens. Right? In a minute, I will run that. I'll uncomment that other line. Oops, sorry. Okay, so let's see. Okay, so that's what you get when you run the program, right? So that should be Q, not S, but anyway. So is the queue empty, right? So remember, Booleans in C are always 0 and 1, right? So 1's true. So is it empty? Yes, it's empty. When you print out the queue, you just get that, right? Enqueue the 0, you get that, right? The size is 1, which is good. Right, you keep on going up to size 5, right, and the queue looks like that. Right, now when you dequeue, right, notice that you're always adding to the back, right, so the queue is growing on the back. When you dequeue, right, everything's coming off the front, right, so when I dequeue the first element, the 0 should come out, right, then the 1 should come out, then the 2 should come out, and then the 3, and then the 4, right. After dequeuing the 5th element, it's empty. If you uncomment that line, right, the assert statement should now come into play, right? So when I try to dequeue the empty queue, it should barf, hopefully. Right, don't forget to make every time, right? Otherwise, you're going to run your program, you're going to get the exact same results if you don't rebuild. Right? Okay, so now, there you go. So there's your assertion. So that's what happens when an assertion fails. Right? When an assertion fails, the assert macro calls abort. Right? So there's a function in C called abort. I think it's defined in standard lib, which will kill the program. Right? And so it immediately stops. It tells you some information. Right? So it tells you where it happened. So on line 62 of this C file, right, this assertion failed, right? And it tells you what the assertion was. Right? And then it aborts. Right? You can turn the assertions off if you want to via a compiler flag, and then this assertion won't happen, and then who knows what happens. Right? So if you remove that assertion from here, right? So if you disable or remove that assertion, then anything can happen. Right? So when you try to dequeue that empty queue, something's going to happen. So the front is going to be null. Right? So when you start to, the front and back will be null. So when you try to do something like freeing, that actually that'd be fine if you free a null pointer. That's actually okay. Is anything going to happen here? Queue size? No, that's actually it'll be okay. It's not going to. So the problem is it's not going to crash, but it's not going to give any indication back to the user either that something wrong has happened. Right? Which is one of the things you have to live with in C. Right? There are no exceptions in C, so there's no way to indicate back. There's no good way to indicate back to the caller that something has happened. All right. Any questions about queues? Anybody? No? All right. That's all I have for today. I'm not sure what we're going to do tomorrow, but we'll find out.